Hey guys, today we're going to look at the current periodic table. So we've already talked about the early periodic tables and how we adjusted our thinking and went through a process of amending and changing our ideas, but now we're going to look at the table as we see it today in depth. So the first thing you need to know is hydrogen. Hydrogen is an element that does not match the properties of any other group, so he stands alone. It is placed above group 1 because he has one valence electron, but he is not actually part of that group. He is a very reactive, colorless, and odorless gas at room temperature. So hydrogen, I like to explain that he has an identity crisis. He is a nonmetal, but because of his one valence electron, he acts like a metal, so we place him near his other metals. Underneath hydrogen, we have our alkali metals, and that is group 1. These metals are extremely reactive because they have one valence electron and they allow compounds to form. So the valence electrons are really important because they are the things that make bonds. When you have very few valence electrons, you really want to get rid of them. And when you have more valence electrons, you really want to fill the empty spaces. So on the either end of the periodic table, we have high reactivities because they're so close to making those bonds that they do it almost instantaneously. These metals, these alkali metals in the first column, are never found in nature in their pure form because of this. Since they are so reactive, as soon as they are put in the wild or as soon as they are seen in nature, they are seen bonded to something else. Because that one valence electron is very easy for them to get rid of. They are silver colored and shiny, and their density is so low that they're soft enough to be cut with a knife. And we'll watch a video in class on this. Group 2 are the alkaline earth metals. They are slightly less reactive than the alkali metals. They are silver colored and they are slightly more dense. So if we can cut the first column with a knife, the second column maybe we'll need a steak knife or a serrated knife. So beryllium, magnesium, calcium, etc. All of those items now have two valence electrons. They're still pretty close to getting their outside shell empty, and they really want to get rid of those two electrons. It just takes them a little bit more effort, so it's a little bit harder to do. And the way that I remember which column goes where, if I look at the name, alkaline, earth, that's two words. So I know that these go in column 2. Alkali metal. Alkali is only one word, so I know that goes in column 1. That's just a way that I remember it personally. Groups 3 through 12. This is the funny short section of the periodic table. These are the transition metals. The metals have a moderate range of reactivity because they have a varying amount of valence electrons. Some of them have 2, so they have the same reactivity as column 2. Some of them have 3, some of them have 4. There is no pretty pattern, so this is something that we're going to use and we're going to look at, but we're not going to look at the transition metals until we look at them very in depth in terms of bonding with names and chemical formulas. In general, transition metals are shiny. All metals are good conductors of heat and electricity. These also have higher densities and melting points than group 1 or 2. So as we move from the left to the right, our metals are getting heavier, they're getting more dense, and they're taking more energy to melt them from their solid stage to their liquid stage. But remember, funny middle section, there is no easy way to tell the valence electrons or the reactivities at this point until we get into a couple units in the future. But keep in mind, every metal on the periodic table is a good conductor of both heat and electricity. After the transition metals, I want to talk about the lanthanides and actinides. These are also transition metals, but these are the two groups that are at the very bottom that are taken out and placed underneath the periodic table just so it's not so wide. Lanthanides are all shiny and reactive. Actinides are all radioactive. So when you look at the actinides on the periodic table, you see that a large majority of them have parentheses around their masses. They do this because since they are radioactive, they actually lose some of their protons and neutrons over time, and when they lose their protons and neutrons, their masses change as well as the element changing. So we call those radioactive elements. You can see them on the periodic table in my room because they are outlined in black with white letters. Now every periodic table shows them slightly differently, but they are the bottom row all the way at the bottom of the periodic table, and it continues through the rest of that bottom row. So on here I have 95 through 103, but they actually go probably from 93 all the way to 118. The ones stopping at 103 are only the ones that are in the actinide section. So again, these are transition metals. They have similar characteristics to transition metals. Some of them are radioactive, and they were only taken out so the periodic table was not so wide. Next is the stair-step line. So on this picture, we can see that alkaline earth, here are the lanthanides and the actinides. These are our transition metals. And we have our regular metals down here again, and then this stair-step line. So on my periodic table in my room, this is drawn with a black Sharpie, so you can see it. On the periodic table that I give you in class, I do not believe it is on there, but on individual periodic tables, it should be. Now again, notice that this has the lanthanides and actinides in the periodic table like normal. Our periodic table has these listed underneath it, and we kind of close this gap here. Okay? This stair step, these are called metalloids or semimetals. They are placed in between the metals, which are all over here, and the nonmetals, which are this top corner. They have characteristics of both metals and nonmetals. They just occur at different times. So if you have boron, boron's this top box right here. At certain temperatures and certain pressures, boron acts like a metal, but it can also act like a nonmetal at other temperatures and other pressures. So that's why they're called metalloids, because they're metals sometimes, but sometimes they're nonmetals also. And we see them used in bonds, and based on the type of bond that they create, it tells us if they're acting like a metal or a nonmetal. And later on, we're going to talk about ionic and covalent bonds. Ionic bonds are metals, covalent are nonmetals. So this stair step, this zigzag line, if you are touching the line, you can be a metalloid. They're not required, because if you see right here, aluminum, he is not a metalloid. And down here, polonium, he is not a metalloid. But if you are touching it, you may be a metalloid. Now we have the top right corner. Our nonmetals are located in this top corner of the periodic table. They mostly exist at gases at room temperature, though one is a liquid and a few are solids. So when you look at the periodic table in my classroom, if they are red letters, that means that it is a gas at room temperature. If they are black letters, that means it is solid at room temperature, and bromine is blue, and that means it is liquid at room temperature. They have varying reactivities as well as characteristics, and they differ a lot. So for example, boron has 3 valence electrons. So based on the gizmo that we've done in class, we have boron with 3 valence electrons. He is more reactive than carbon, who has 4 valence electrons. Boron only needs to kick 3 out. Carbon needs to fill the other 4 spaces in his outside shell, so he's going to share electrons in order to make that happen. But since he's only halfway there, it's going to take him a little while to do it, so he's not overly excited or anxious. Nitrogen, on the other hand, has 5 valence electrons. He only has 3 more spaces to fill, so he's more reactive than carbon is. Oxygen only has 2 spaces to fill, so he's more reactive than nitrogen is. And fluorine only has 1 space to fill. So in class, we're watching that video on alkali metals, and the alkali metals only have 1 valence electron to give away. This column underneath fluorine, column 17, are called halogens. They only need 1 more valence electron, so they are just as reactive as column 1 is, because they are so close to filling their outside shell. So columns 1 and 17 tend to bond together. Columns 2 and 16 tend to bond together, etc., etc. So remember, the reactivities, they start high and they decrease until they hit the column 14. These are the ones right smack dab in the middle, and then the reactivities increase again. So group 17 are halogens. These nonmetals are gases at room temperature when they exist as diatomic molecules. And diatomic molecule is a fancy way of saying 2 of the same atoms bonded together. So Cl2 is chlorine, but there are two chlorines bonded to make that molecule. Single atoms of these often form salts with groups 1 and 2, like I just said on the previous slide, because 1 and 2 really want to get rid of their 1 or 2 valence electrons, and group 17 really wants to fill their last spot. So we may have 1 beryllium with 2 valences bonding with 2 fluorines, because these electrons are going to end up bonding together, and these electrons are going to end up bonding together. So it's possible that we do pair up with other columns than 1 and 17 and 2 and 16, and we'll get to that later. Group 17 are considered the most reactive nonmetals because they will always be paired together or bonded with a metal. You will never see group 17 as a single fluorine or a single chlorine atom. They will always be either a diatomic molecule, Cl2 or F2, or they will be a salt formed with group 1. They do not exist as single monatomic atoms in nature. Finally, we have group 18. These are the noble gases. Column 18 only exists as monatomic atoms. They do not bond with anyone because their outside shell is full. So in previous notes, we saw that hydrogen and helium fill the first shell, and you may only have 2 electrons in the first shell. Lithium through neon can hold 8 electrons in their outside shell. So neon has all 8. Since he has all 8, he cannot bond with anyone else. Same with argon, same with krypton, same with xenon, same with radon. Helium is put over that column. He only has 2 valence electrons, but he has a full outside shell, so he acts exactly the same as everyone beneath him. So since they are all full, they are completely unreactive. The science term for that is inert, with all elements. So even if they were thrown into a mix with other elements that are unbonded, that are by themselves, they will still not create a bond with them. Noble people from medieval times or old times, they think that they're better than everyone else, so they don't mix with the general public. So that's why I think of that last column, because they act like old-time nobility. They will not bond with anyone, no other elements, and not even atoms of their own element. So when we get to class tomorrow, you're going to be practicing with the periodic table. We're going to be looking at characteristics, we're going to be looking at relationships, and we're going to be doing activities to help us figure out other things on the periodic table that are trends and characteristics that we will see. So I'll see you tomorrow so we can work on this.